In section 5.2, we're looking at the definite integral, and we'll start by defining that. But one of the things I want to write down before we get to that definition is something that we left off with in the last section, and that was the Riemann sum, which gave us area. The area under f of x from x equals a to x equals b is given by the limit as n goes to infinity of the sum from I equals 1 to n f of xi delta x. What we're going to do is define this area as a definite integral. So the definite integral of f from a to b is given by, first I'm going to write how we write the definite integral. So we have our integral symbol that we saw from the antiderivative section, but since we're going from a to b, we put those limits on there. So we put the a and the b as lower and upper limits on the integral symbol. We have our function f of x dx. And we're going to define this to equal the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. So this definite integral thing that we're defining can be interpreted as area under a curve. Okay, so once again, before we get going too far, I'd like to point out some of the pieces of this thing. So when I write our integral symbol ab f of x dx, I just want to remind you of what all these pieces are and introduce the new ones. The a and the b are called the limits of integration. So the one on the bottom is the lower limit of integration, and b, or the number on top, is the upper limit of integration. Okay. This elongated s is our integral symbol. Then we have our function, and then that differential dx lets us know the variable of integration. Similar to our integrals that we were talking about in the antiderivative section, but now we have these limits of integration. The other thing is, what we've defined here has nothing to do with a derivative. We're defining it based on this limit of a sum that gives us an area thing. In the next section, we'll see how these two connect. But for right now, we're just going to think of it as this limit of a sum and go from there. When we talked about derivatives, remember that one of the first things that we talked about was, when can I take a derivative of a function? And we said the derivative existed, and I wrote out that limit definition. The derivative exists when the limit exists. Well, the same thing is true here. The function f of x is said to be integrable on the interval ab if this limit exists. Well, how do we know when the limit's going to exist? We'll have our first theorem. If f of x is continuous on the interval ab, then f is integrable on the interval ab. All right, let's look at an example of computing an interval, an integral. In the last section, we looked at the function y equals x squared on the interval 0 to 2, and we came up with two different approximations for that integral, one using left-hand endpoints and one using right-hand endpoints, and that gave us a lower and upper limit for, an overestimate and an underestimate for the area under the graph. So now we're going to find the exact area because our integral is defined by this limit, and this limit, we said, is defined to be the area under the graph. So let's walk through how to find an integral using the limit definition. And that's the key part here. In the next section, we'll figure out a shortcut method, just like we did for derivatives. But right now, we're going to see if we can do this using that limit definition. So I'm going to start by writing out the limit definition, right? The integral from 0 to 2 of x squared dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. So let's write out what these pieces are. We know a formula for delta x, that's b minus a over n. And we know a formula for xi, that's a plus I delta x. In this problem, because we're integrating from 0 to 2, the a is 0, the b is 2, and the function f of x we can see as x squared. So delta x is 2 minus 0 over n, which is 2 over n, and it stays 2 over n. I don't have a value for n. N is going to end up going to infinity. and xi is 0 plus I times 2 over n, which is 2I over n. So f of xi is f of 2I over n. Since my function is x squared, this will be 2I over n squared, which is 4I squared over n squared. Okay, so let's plug in our pieces. So we have the limit as n goes to infinity of the sum from I equals 1 to n. F of xi we just found was 4I squared over n squared, and delta x is 2 over n. Okay, so 4I squared over n squared times 2 over n will give me 8I squared over n cubed. And now it's really important here that I keep track of what my variables are. I have an I and I have an n. I have a sum, I have a limit. Different things are happening at different times. In the sum, I'm adding up terms. I start with I being 1, plus the next term is when I is 2, and the next term is when I is 3, and so on. Everything else stays constant with the sum. It's the I that's the variable. So the 8 over n cubed is a constant. We can factor that out of the sum. So I have an 8 over n cubed times the sum from 1 to n of I squared. Now, if you recall, when we were going through the properties of sigma notation, we had this formula that the sum from I equals 1 to n of I squared was n times n plus 1 times 2n plus 1 all over 6. So I can look at this sum now from 1 to n of I squared and say, I have a formula for that. Plug that in. So there's the n plus 1, 2n plus 1 over 6. Okay, now this is what the formula I think looks like in its neat form. But what I want to do is write it out in its FOILed out form. So I'm going to go ahead and FOIL this out. So 2n times n gives me 2n squared, but I have an extra n in here. So we'll have 2n cubed plus n plus 2n gives me 3n, and then times another n is squared. And then 1 times 1 gives me 1, and then multiplied by an n gives me an n. So I think that this is going to be a more useful way to write my formula. Okay, so let's take a couple steps and do this very slowly so we can see exactly what's going on. I'm going to distribute the 8 into the numerator. So we'll have 16n cubed plus 24n squared plus 8n. And in the denominator I have 6n cubed. In the past, when we were looking at limits as x goes to infinity, we picked the biggest power of x in the denominator, and we wanted to divide it in the numerator and denominator of the big fraction. So in this case, n is going to infinity. I do the same thing, except with the n's. So I'm going to multiply by 1 over n cubed in both the numerator and denominator. So we'll have 16n cubed over n cubed plus 24n squared over n cubed plus 8n over n cubed. That's our numerator. And in the denominator, we have 6n cubed over n cubed. So the n cubes cancel. N squared and n cubed will leave an n in the denominator. N and n cubed will leave an n squared in the denominator. And here the n cubes cancel. As n goes to infinity, dividing by n is going to go to 0. So this is going to be 16 plus 0 plus 0 all over 6. And 16 over 6 is the same as 8/3. So the exact area is 8/3. All right, let's look at another example. In this one, we want to find the definite integral from 3 to 6 of the square root of 9 minus x minus 3 squared, all under a square root. This integral, what we're going to do, rather than going through that full limit definition, we're going to be a little bit clever. What we're going to do is recognize that the graph of y equals the square root of 9 minus quantity x minus 3 squared is a semicircle. Maybe a way to see that is if I squared both sides, and then I added that x minus 3 term to the other side, I'd have y squared plus x minus 3 squared equals 3 squared, and that's like the equation of a circle. Okay, replacing the x with an x minus 3 shifts the circle to the right 3. And since it's equal to 3 squared, I'm going to have a radius of 3. So this is going to be a circle of radius 3, centered at 3, 0. But I only get the top half because my original equation was y equals the square root. Square roots always output a positive, so my y values should always be positive. So this is the graph that I'm looking at, and we're finding the integral from 3 to 6. That's this area here. That's the area of 1/4 of a circle of radius 3. But circles I know how to find area of. The area of a circle is pi r squared. For a circle of radius 3, it would be 9 pi. What I have is exactly half of the top half of the circle, which is 1/4 of the circle. 1/4 of the circle has area 9 pi over 4. So the integral from 3 to 6 of the square root of 9 minus x minus 3 squared dx is equal to 9 pi over 4. Okay, so sometimes we can be clever. Let's look at another example. Let's look at the integral from -2 to 1 of x cubed dx. So you don't need a graph in order to find the value of an integral, but I'm going to graph this anyway, just so we can see what's going on, and because I want to point something out when we're finished with the problem. Okay, so we're looking at the integral from -2 to 1, and so we're going to have this area here. Let's go ahead and work this out using the limit definition. So the integral from -2 to 1 of x cubed dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. Let's find our pieces. Delta x is b minus a over n. The b is 1, the a is -2. So 1 minus -2 is 3. The formula for xi is a plus I delta x. A is -2, so I have -2 plus I times 3 over n, which is -2 plus 3i over n. So f of xi is -2 plus 3i over n cubed. I'm going to, over here on the side, work out what this is. I'm going to go ahead and FOIL that out, or expand that out. You could do this quickly if you're familiar with the binomial theorem, since most of you probably aren't fresh on the binomial theorem. We'll do this the long way. I write out -2 plus 3i over n. It's 3 factors, and I'm going to FOIL it out, simplify, and then FOIL out again. So in the first one, -2 times -2 will give me 4. -2 times 3i over n is -6i over n. 3i over n times -2 is minus another 6i over n. And then 3i over n times 3i over n will give me a 9i squared over n squared. Okay, so I want to simplify a little. -6i over n minus 6i over n will give me a -12i over n. Okay, now we expand again. So I'm going to take each one of these times -2. So 4 times -2 is -8, plus 24i over n minus 18i squared over n squared. Now I take each of these terms and multiply it by 3i over n. So we have plus 12i over n minus 36i squared over n squared plus 27i cubed over n cubed. gather our like terms. So we have 24I over n plus 12I over n will give us a 36I over n. And then negative 18 minus 36 will give us a minus 54I squared over n squared. And then our 27I cubed over n cubed stays the same. Okay, that will be helpful when we plug in over here. So I have the limit as n goes to infinity of the sum from 1 to n, f of xi, which I have a simplified version of that now, times delta x, which is 3 over n. Okay, let's go ahead and distribute that 3 over n. So I have minus 24, lost the sum. So I have negative 24 over n plus 108 I over n squared minus 162 I squared over n cubed plus 81 I cubed over n to the fourth. Here's where we're going to really employ our properties of that sigma notation. What I'm going to do is say I have a sum of 4 things added. I can break that up into 4 separate sums. So we have the sum from 1 to n of negative 24 over n plus the sum from 1 to n of 108 I over n squared plus the sum from 1 to n of negative 162 I squared over n cubed plus the sum from 1 to n of 81 I cubed over n to the fourth. And now I'm going to use another property of sigma notation, and I'm going to take any constant multiple that I can and factor it out. So in the first one, well, the first one I can factor it out or not, it doesn't really matter, but I'm going to go ahead and factor it out, 24 over n, and I'm left with a factor of 1. The second one, the 108 is a constant, and remember the n is constant relative to the sum, not constant relative to the limit, but for the sum, the n is not changing from one term to the other. So for each one of these, I'm going to take out the constant and the n and just be left with the i's. Okay, now let's remember all of our summation formulas. The sum from 1 to n of 1 is just n. The sum from 1 to n of I, we worked that out. That was Gauss's little discovery. So that's n times n plus 1 over 2, but I'm going to write that as n squared plus n all over 2, but I can even write those as separate fractions. We'll see why in a minute. Okay. The sum from 1 to n of I squared, if you remember back, just an example, we said we could write that as 2n cubed plus 3n squared plus n over 6. And then finally the sum from 1 to n of I cubed, we said was n times n plus 1 over 2, and all of that is squared. So if I expand that out and then square it and simplify, I will get n to the fourth over 4 plus n cubed over 2 plus n squared over 4. All right, so let's bring these in. So I have a negative 24 over n, and I'm multiplying that one by just n. For the next term, I have 108 over n squared, and I'm multiplying that by n squared over 2 plus n over 2. And I have a negative 162 over n cubed times, if I write this as 3 separate fractions, that will be an n cubed over 3 plus n squared over 2 plus n over 6. And finally, we have the 81 over n to the fourth times n to the fourth over 4 plus n cubed over 2 plus n squared over 4. A couple more steps. This first one I can just cancel the n's and we're good. The next one I'm going to distribute. And distribute. And distribute. So the negative 24 is just there. This first one I have 108n squared over 2n squared plus 108n over 2n squared, negative 162n cubed over 3n cubed, negative 162n squared over 2n cubed, negative 162n over 6n cubed. Okay, last set. 81n to the fourth over 4n to the fourth. 81n cubed over 2n to the fourth. 81n squared over 4n to the fourth. Okay, I only want to cancel the n's right now because there's too much other stuff going on. So after I'm done canceling the n's, I'm going to go ahead and find the limit by letting any term with an n in the denominator go to 0. So I have negative 24 plus 108 over 2. Here I have an n in the denominator, so that becomes a 0. Minus 162 over 3 plus a 0 plus another 0 plus 81 fourths plus a 0 plus 0. And I'm going to skip past the simplifying fractions. When I add all of this together, I get negative 15 fourths. Or if you want to write that as a decimal, negative 3.75. Okay, two things. First of all, I'm now done. I've computed the integral. Second, I thought that integrals were an area, and I have a negative number here. Negative area does not make sense. So we have to figure out what's going on and why did we get a negative. Coming back to my graph, if I think about drawing rectangles, on the right-hand side, these rectangles above the x-axis will have a y value that's positive. On this left-hand side, if I draw these rectangles, the function value is negative. When I'm looking at area, I don't look at whether or not a length goes above or below the x-axis. I just look at how long the side is of a rectangle. But in our formula, that's not what we have. We have the function value, not the length of a side of a rectangle. So although that we can compute the area under a curve and interpret it as a definite integral, we can have definite integrals that are not really an area. We can have this craziness with negatives going on. So let's talk about that for a second. So let's look at integrals and net signed area. When I look at the way that our integration formula is formed, the integral from a to b of f of x dx, I'm taking the limit of a bunch of rectangles. And as we saw in the last example, if I have a curve that is sometimes below the x-axis and sometimes above, then the stuff that's below the axis, call this area 1, and the stuff that's above the axis sort of behave differently. Call this one area 2. Okay, so if I were to compute this integral, and let's suppose that this is a and b here, when I go to compute this integral, what I'm going to get is a2 as an area would count positive, and a1, the area would count negative. So this would give me a2 minus a1, which isn't really my area. This is I'm looking at a1 and a2 as being signed area because stuff below the axis counts negative. And when I look at the difference, I get what's called net signed area. If I want my integral to compute exactly the area, then what I do is I put an absolute value on my function. That way my function is never negative. So that would give me a2 plus a1, which is the actual area. However, it turns out that this whole net signed area business is actually much more useful in most of the applications that we use. And in the places where we really want just a straight up area, we can always just throw the absolute values in there. So this business of counting the stuff below the axis as negative turns out to be helpful. Okay, so let's use this to give us some properties of the definite integral. here's our first property. If I take the integral from a to a of f of x dx, I'm looking at a region where I start and end at the same place. So I don't have a two-dimensional region that we're covering because we start and end right away. So there's no area there. So I just get 0. Next, if I take the integral from a to b of a function, that is the opposite of taking the integral from b to a of that function. So in this case, what we can do is say, or maybe a good way to imagine this, if I have some function, and it doesn't matter if it's positive or negative, but it goes from a to b, when I integrate from a to b, I'm counting up one direction. If I integrate starting at b and go to a, I do the same process in reverse, and so I get a negative on there. It's kind of like what we did with net signed area, except it would be the width of the rectangles that counts as negative instead of the height. Next, if I integrate from a to b and I have two added functions, then I can just break that up into two separate integrals. If I have two functions stacked on top of one another, I can just add up the areas separately. Give me the area of the stack. Next, if I have a constant multiple, I can factor that out. Now this last one is going to be a confusing one, so we're going to spend a little time going over that. If I have the integral from a to b of f of x dx, I can write that as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. What I want to do is draw you a picture to illustrate what's going on with this last one. Okay, so here's a graph. Let's suppose I have some function. I have an a and I have a b. So the integral from a to b of f of x dx is all of this area. Let's suppose there's a c that's in between. I can write this as the integral from a to c plus the integral from c to b. And when I add those two areas up, I get the same areas I started with. So when c is in between a and b, this makes perfect sense. However, because of net signed area, I don't need the c to be in between the a and the b. So let's look at another possible scenario here. Here's my a, here's my b. And let's suppose the c is out here to the right somewhere. Okay, the integral from a to b is still going to be this blue shaded region. Now, the integral from a to c is going to be in green. So I already have more area than I want. However, the integral from c to b, because I'm moving backwards, is going to count negative. So this portion here counts as negative and will cancel out the extra area that we ended up adding up. So I end up with a net area of just from a to b. And the same will be true if the c is to the left of a. So this property does not have any conditions on c. C can be anything we like, as long as the integral is defined over the interval. So let's look at an example. Suppose that the integral from 0 to 4 of f of x dx is equal to 6. The integral from 0 to 3 of f of x dx is equal to, we'll say, 2. Find the integral from 3 to 4 of f of x dx. So here's how I would go about this. I would say that the integral from 0 to 4 of f of x dx, using that last property that we just had, I can break that up into two integrals, where I can put any c in there that I want. So what I'm going to do is I'm going to insert a 3 in between the 0 and the 4. So I'll say this is the integral from 0 to 3 of f of x dx, plus the integral from 3 to 4 of f of x dx. Now what I'm going to do is I'm going to substitute in the values that I know. The integral from 0 to 4 of f of x dx we were given as 6. The integral from 0 to 3 of f of x dx we were given as 2. And then this is the piece that we want to find, the integral from 3 to 4 of f of x dx. So if I just subtract 2 on both sides, then I find that the integral I'm looking for, the integral from 3 to 4 of f of x dx, is just equal to 4. The last piece that I want to talk about in this section is the average value of a function. So we'll start with the definition. The average value of f of x on the interval a, b is given by 1 over b minus a times the integral from a to b of f of x dx. So what I'd like to do is maybe give you an intuitive sense for what we're talking about here. If I want to add up some numbers, or if I want to find the average of a set of numbers, right? So if I take the average of 2, 4, 7, 9, 12, the way that I get that average is by adding up all the numbers and then dividing by how many of them I have. If I had infinitely many numbers that I wanted to find the average of, this would break down because I can't add up infinitely many numbers. I would get infinity. And then if I divide by how many I have, that would also be infinity. I have infinity over infinity, so that I get nothing. However, when we look at an integral, we have effectively added up infinitely many of something, right? We've added up infinitely many rectangles in order to find that area. So we can leverage that for, in general, just adding up infinitely many things. Okay, and that's kind of what we're doing here when we find average value of a function. It's like averaging infinitely many numbers. Okay, what we're going to do is we're going to say, suppose I have some function on an interval from a to b, and I want to find the average value or average y value or average height of that function. One way to think about it is if I took every possible x value and found its y, its corresponding y, that would be a list of y values that I could average together. Except that from a to b, there's infinitely many of them. Okay, but that's what finding the area does. It adds up all of those heights of the rectangles, right? So if I think of each rectangle is f of xi times delta x, then if I add up all of the rectangles, right, I've added up all of these products. The area is the sum of f of xi delta x. But the delta x is the same, right? We know that we can factor that out. Add up all of the delta x's, right? The delta x is just the width of the rectangle. Well, if I add up all of those widths, I get the interval a to b. If I think about the area divided by delta x, then I'll just think of like the sum of the f of xi's. So adding up all of those delta x's is like the interval a to b. So that's this, the length of the interval is b minus a. So that's where this 1 over b minus a comes from. I'm dividing out the width. And then if I take the area and I divide by the width, that's just giving me the heights added up. Okay, and that's this notion of average value. Okay. Another way to think about this is if I take a little bit of a geometric point of view and imagine this, okay, this area here, and I put solid walls on the side, on my A and on my B. Solid wall. Now imagine that that area is made of like ice or something like that, and I let it melt so that the top part melts and flows down into the bottom part. And what will happen is when it turns into water, it will level out to some height. Okay. And that height is the average value. Okay, so that's just an intuitive notion of average value. We'll make use of that a little bit in this section and then more in the future. That's it for 5.2.